Hello, we are in 2.6, the last section of Unit 2, which is all about systems. So, linear programming. This is going to be your application section, kind of tying everything together, but it's really the application of the systems of inequalities, which was our 2.5 section. So, we want to know, how do we find maximum and minimums of feasible regions in these real world problems? So again, real world problems almost always translate into word problems when we're talking about math. So a couple of things that I want to show you step by step what we're going to do when we're working with a linear programming problem. First step is that we need to define our variables. That's pretty standard across the board. Anytime we're dealing with a word problem, we have to define our variables. The second thing we need to do is write the objective function. And this is going to make more sense once we're actually doing a problem. The first example on our notes, they actually give us the objective function. But whenever I give you a word problem, you might have to figure out the objective function. Step 3 is that we're going to write our constraints. The constraints are going to translate into our system of inequalities. So constraints being like, maybe the amount of M&Ms that I'm using in the recipe cannot be more than this amount or whatever. So depending on the problem that's given, your constraints will come from there, and that will be your system of inequalities. So if that's my system of inequalities, then obviously the next step is to graph that. And so when we're graphing these multiple constraints, these multiple inequalities, shading is going to be all over the place. So we're going to find the area where the shaded region is our answer. Okay, we call that the feasible area. So what we do after that is we find the vertices of that feasible area. So of that shaded region, we could have 3 vertices, 4, 5, just depending on the shape of that feasible area. Then we're going to take those vertices, plug them into our objective function, and then depending on what the question is asking, that's when we'll answer the question. So it might want the minimum, it might want the maximum, it might want both, it might want the average. It just kind of depends on the question. So example 1 is not in a word problem format, but it walks you through kind of these steps. So it says, find the minimum and the maximum values of C equals 4x plus y with the following constraints. So this means this C equals 4x plus 5y, that's our objective function. This is the objective function. Okay, and it gives us our constraints. And notice it's listed as a system. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. And x plus y has to be less than or equal to 6. Well, I'm not defining my variables because this is not a word problem. The objective function was given to me. The constraints were given to me. So step 4 says I need to graph those inequalities. So I'm going to graph x is greater than or equal to 0. So that's going to be a vertical line here. And I would be shading to the right of that line. Y is greater than or equal to 0 is going to be this horizontal line here. And I will be shading above. So as of right now, this entire quadrant is shaded. And then the last one is x plus y is less than or equal to 6. So what I need to do is I need to subtract my x over so that I now have y is less than or equal to negative x plus 6. So then that means I have a y-intercept of 6. So I'm going to count by ones. 1, 2, 3, 4, 5, 6 is here. 1, 2, 3, 4, 5. And then it's a negative 1 slope. So boom, 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 boom. It is a solid line. And this would be shaded below the line. So if I'm shading to the right of the vertical, above the horizontal, and then below this diagonal line, that means my shaded region is here. Okay, so this is my feasible area. And so what I want to do next is I want to list out the vertices of that feasible region. Well, this feasible region is in the shape of the triangle. So it's going to have 3 vertices. One of them is at 0, 0. One of them is at 0, 6. And one of them is at 6, 0. So those are the 3 vertices of the shaded region. So now what I need to do, I found my vertices. Step 6 says plug the vertices into the objective function. Well, I know what my x's are, I know what my y's are, so the values of c. So I'm going to go in order. I'll plug in 0, 0 first. That would translate into c equals 4 times 0 plus 5 times 0, which is obviously going to give me a cost of 0, or whatever c is representing. Okay. Then I go to maybe 0, 6. C is equal to 4 times 0 plus 5 times 6, which is going to give me a C value of 30, because 5 times 6 is 30. And then the last one is 6 and 0. So C is equal to 4 times 6 plus 5 times 0, which is going to give me a C value of 24. And so my last step is to answer the question. The question wanted the minimum and the maximum value. So the minimum value out of 0, 30, and 24 is 0. And that value comes from when x is 0 and y is 0, because it was the point 0, 0. The maximum value out of those 3 things is 30. And that was when x was 0 and y was 6. So in a problem, depending on what x and y are representing, then it might say, what is the maximum cost? So, well, that might be, when I have 0 of this and 6 of that or whatever. And so now we'll kind of get into that problem. Here is a word problem. And so notice I am kind of guiding you for this one. I put step 1, define the variable. Step 2, what's the objective function? Step 3, the constraint. Step 4, graph. Step 5, yada, yada, yada. I'm not always going to give you those steps flat out, but this is your note, so I want to guide you through it, okay? So we just have 2 problems that we need to do. And so let's go green. Here we go. A school is investigating various ways of composing faculty for a proposed new elementary school. They hire teachers and aides. The amount of money spent on salaries each year depends upon how many teachers and how many aides are hired. The board finds that the average teacher salary is $30,000 and the average aide's salary is $20,000. The board has the following requirements for the number of teachers and aides allowed. The building can accommodate no more than 50 faculty members. The school must have a minimum of 20 faculty members. There must be at least 12 teachers. For a proper teacher-to-aide ratio, the number of teachers must be at least half the number of aides. Determine the number of teachers and aides that would represent the minimum cost to the school district. So yes, I understand that this is a lot of information, okay? Notice the way that it's set up with the board has the following requirements. These are all going to be your constraints, okay? This is going to give us some inequalities to follow and to graph. What I need to do first is define my variables. In the problem, the first thing they kind of talk about is the salary of the teacher and the aide, but that's not going to be what my variables are going to represent. My variables are going to represent the number of teachers and aides, because that's really my end goal, is to determine how many teachers and how many aides will represent the minimum cost to the school district. So I'm going to say that X is going to equal the number of teachers that this district hires, and Y is going to be the number of aides. And you are more than welcome to use T and A if that makes more sense to you, but I will be using X and Y here. What our objective function is we need to decide what of those number of teachers and what of the number of aides will represent the minimum cost to the school district. So that's our question, right? Our answer needs to be how many teachers, how many aides give us the minimum cost. So our objective function is going to be the cost is equal to $30,000 for every teacher, because that's their salary, plus $20,000 for every aide. That's their salary. And so if I know the value of X and I know the value of Y, then I can get that cost for the school district. If that's the only thing that they're, worried about is the salary. Okay. So that's the objective function. Next thing I want to do is write those constraints. And like I said, those requirements are the constraints. If the building can accommodate no more than 50 faculty members, then that means the number of my teachers plus the number of my aides has to be less than or equal to 50. It says no more than 50. Well, that means we can have 50 and we can have less than that. We just can't have more than that. So X plus Y is equal to 50. I know that because I'm going to have to graph these things next, I can go ahead and rewrite this as Y is less than or equal to negative X plus 50. I'm writing out my system here. Okay. The next constraint says the school must have a minimum of 20 faculty members. So that includes teachers and aides. So the number of teachers and the number of aides has to be a minimum of 20. So that means X plus Y has to be greater than or equal to 20. I can have 20 and anything more. I just can't have less than that. So it's somewhere between 20 and 50 faculty members. Again, I know I'm going to have to graph this, so I can go ahead and rewrite as Y is greater than negative X plus 20. Another requirement says there must be at least 12 teachers. Well, the number of teachers is X, so that means X needs to be greater than or equal to 12. At least 12 teachers. Can I have 12? Yes. Can I have more than that? Yes. Can I have less than that? No. So X is greater than or equal to 12. And then the last one says for a proper teacher to aide ratio, the number of teachers must be at least half the number of aides. So the number of aides is half the amount of teachers. So the number of teachers has to be half the amount of aides. And it says at least half the amount. So this has to be greater than or equal to. You can rewrite that if you want to, because it'll be hard to graph this. So if I want to solve for Y, I can multiply both sides by 2, and I'd be getting Y is less than or equal to 2X. Okay. You're dividing by half, which is the same thing as multiplying by 2 to get Y by itself. And so here we have 4 constraints that we need to graph. Now, they didn't say this specifically, but it is something that you always kind of want to be sure of is like X is greater than or equal to 0, Y is greater than or equal to 0. It doesn't specifically say that we have to hire some teachers and we have to hire some aide members, but that's the whole point of this problem. So we have that X needs to be greater than or equal to 12, but it might make sense for us to also incorporate that Y needs to be greater than or equal to 0. I have to have some aides, right? If I have teachers, I have to have some aides. So here we go. Next step, graphing this, okay? So I want to make sure that my the way that I count, my scale of the graph is going to fit what I need to see. And so my biggest y-intercept, my biggest number is 50, so I cannot count by ones to do that. You could count by twos, but again, you wouldn't get all the way up to 50. So I'm going to go ahead and count by fives. It'll be a little bit more spread out than tens. So I'm going to count by fives. So I'm going to call this my 5, 10, 15, 20, 25, 30, 35, 40, and then 50. And I'll do the same scale because if I don't do the same scale, I almost always mess up. You don't have to do the same scale, but it's just easier that way in my opinion. Obviously, this is 0, 0. Okay, so I'm going to start from the top. Y is less than or equal to negative X plus 50. So I'm starting at 50. I'm using a -1 slope. So I know that it's going to have this. And it is a solid line because it's less than or equal to. And so here I am. Now, I'm not going to shade just yet, but if I'm shading, if y is less than or equal to negative x plus 50, that means I'm shading below this line. So somewhere in this area, right? Okay, I go to the next one. Y is greater than or equal to negative x plus 20. So 20, negative x slope, solid line again, but this time I'm shaded above. So if I'm keeping track, as of right now, my shading is in the middle. This is no longer, right? Because it has to be for both. Then I'm going to graph x is greater than or equal to 12. Well, that's a vertical line. Now, because I counted by fives, I'm going to have to kind of estimate here, but I'm going to say it's about right there. Ooh, that was, oh, come on. Try that again. It's about right here. There we go. Thank God for that thing of notability. All right. And then it said x is greater than or equal to that. So I'm shading to the left. So as of right now, my shading is here. But I have a couple more left to graph. The last one is y is less than or equal to 2x. So that means I have a 0 y-intercept up to over 1. So I'm dealing with this line here. I know it's a solid line again, and that one is less than, so I'm shading below. So right now, my shaded region is here. Okay, I also have, like I said earlier, technically I have that y is greater than or equal to 0. So really along this axis, everything shaded above that, which makes sense for the problem. So my final shaded region is in this feasible region. This is my region. Okay, it is not a triangle like last time. Okay, this actually has 1, 2, 3, 4, 5 sides. So it's some kind of pentagon, an irregular pentagon. And it has 1, 2, 3, 4, 5 vertices. Okay, and so that is my feasible region. So I need to write those vertices out. So I have a vertex here, 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 and here. Okay. Unfortunate for us, some of those are not at perfect grid lines. Some of them are. The easier ones, obviously, we see we have 20, 0 and 50, 0. So those are going to be easy. 20, 0, 50, 0. Okay. The ones that I have along this line right here, I know the value of x is going to be 12. So it's 12, something and 12, something. And then this last one over here, I don't want to estimate that. I don't know exactly what it is just yet, so I'm going to have to use some algebra skills. So let's go back to the ones where we do know those x values of 12. And so what we do to find those intersection points is we set those two equations equal to each other. So I know that I'm getting, I'm using x is 12, and then I'm also using for, let's go with this point first. That other green line that it's being intersected with is the y is equal to negative x plus 20. And so if I know what x is, I can plug that in. And so I'm getting negative 12 plus 20, which means y is going to be 8. So this point right here is 12, 8, which makes sense on my graph. It looks like it's at 8, and so that makes me feel good. I know I did my math right. Now I'm going to go to this point here. I'm doing the same thing. I know my x value has to be 12, but this time it's intersecting with the line that is this one right here. That would be the 2x line, right? So x is 12, 2 times 12 is 24. So this point is at 12, 24. Again, that makes sense on the graph. It's right below 25. So 12, 24 is another point. And then lastly, I have this one right here. I do not know the x and I do not know the y value. I cannot assume, I cannot estimate here. But what I do know is that I know that it's using the 2x line and the negative x plus 50 line, and it's where they're intersecting. So then I need to set those two things equal to each other, solve for x, plug it back in, and solve for y. So solving for x, I could add my x over. I'd get 3x equaling 50. Dividing by 3, I get 50 over 3. So my x value for that point is going to be 50 over 3 comma something. Now, what is that something? I can plug this value of x in here, or I can plug it in here. Work smarter, not harder. It shouldn't matter which one you plug it into, but I'm going to go with 2x. Well, if x is 50 over 3, and I multiply that by 2, I get 100 over 3. So that ordered pair is 50 thirds and 100 thirds. Okay, so when you are finding a vertice and it's not on a nice solid grid line, you cannot estimate. You have to algebraically find it. You're going to use the intersection of the two lines where that point is and set them equal to each other. Okay, so here are our 5 vertices. The next step in the process is plugging the vertices, into our objective function. Our objective function was talking about the cost for this district. $30,000 for each teacher, $20,000 for each aide. Well, now that I know the vertices of my feasible region, I need to plug in each vertice into that objective function because I need to answer the question, which one is going to give me the minimum cost? Minimum, smallest. Okay, so I plug in those vertices. Let's say I start with 20 comma 0. Then that means I have C equals 30,000 times 20 plus 20,000 times 0. That's going to give me a cost of 600,000. Okay, now I'll go to 50 comma 0. 30,000 times 50 plus 20,000 times 0. That gives me 1,500,000. Then I go to the next one, 12/8. Cost $30,000 for 12 teachers, $20,000 for 8 aides. Okay, I plug that in my calculator. I get $520,000 for the district. I keep going. I have 12 and 24. Okay, I'm going to take over this space right here. 12 and 24. My cost, $30,000 for 12 teachers plus $20,000 for 24 aides. That gets me $840,000. And the last one, 50 over 3, 100 over 3. Cost $30,000. Yeah, $30,000 for 50 over 3 teachers. Now, hopefully you're thinking to yourself, can you hire 50 over 3 teachers? No, you cannot. Okay, so this would not be a realistic answer. However, it is one of the vertices. It is something that we need to test, but we know that doesn't make sense. Okay, so and then 20,000 for 100 over 3, and that would give us a cost to the district of $1,166,667. Okay. What the question was asking was which one is going to represent the minimum cost. Well, out of these numbers, which one is the smallest dollar amount? 520,000. That's when we had 12 teachers and 8 aides. Okay. If it also asked for the maximum, then we would have chosen this one, 50 teachers and no aides. Okay, just FYI. But all it wanted was the minimum. And so there you have it. I know that took a long time. It's a lot of information. But if you break it down and remember these steps, then it should be extremely easy for you. Okay? Let's try it one more time. I was using Barney colors, I just noticed. All right. Judah works in a bakery and is making pies and cakes. He makes a $15 profit on each pie and a $12 profit on each cake. Every pie he sells requires 15 minutes of work and 2 cups of sugar. Every cake he sells requires 10 minutes of work and 3 cups of sugar. Judah has 24 cups of sugar left in inventory and has 2 hours to work before the store opens. Due to a typical demand, he must make at least twice as many pies as cakes. He also must make a minimum for 2 pies due to a pre-order. How many of each type should he make to maximize profits? Even though this problem is shorter just by looks, I find it to be more difficult because you are now talking about the number of pies, the number of cakes, the profit of a pie, the profit of a cake, 15 minutes of work for a pie, 10 minutes of work for a cake, 2 cups of sugar here, 3 cups of sugar here. You have a lot of different quote unquote variables to this problem. So with that being said, what are your 2 variables going to represent? Is it going to represent the amount of pies and cakes, the minutes of work for a pie and a cake, the profit of the pie and the cake, the cups of sugar for the pie and the cake, right? You have to think about these things. Go to the question. The question is asking, how many of each type should he make to maximize profits? How many of each type? There's your giveaway. That means your variables need to represent the number of pies and the number of cakes. Okay? So I'm going to use X and Y again. X is going to be the number of pies. Y is going to be the number of cakes. Okay? Our objective function also goes back to the question at hand. Our answer is going to be how many of each type, but our objective is to figure out him maximizing his profits. That has to do with money. So that means we're going to use the $15 profit for the cake and $15 profit for the pie and $12 profit for the cake. So his cost, the objective function is $15 for every pie and $12 for every cake. Okay. So now I go and I think about sugar and work and all that stuff. So pie, 15 minutes of work. Cake, 10 minutes of work. Then I have, let's go lime green. Then pie is 2 cups of sugar. Cake, 3 cups of sugar. Okay. Sugar. Time. Okay. So, hopefully color coding will kind of help us here. Write the constraints. So those are our constraints, is the amount of time and the amount of sugar, etc., etc. Let's say we start with time. 15 minutes for each pie, 10 minutes for each cake. He only has 2 hours to work. Pause right there. Red flag should be going off. 15 minutes of work for a pie. 10 minutes of work for a cake. He only has 2 hours to work. How many minutes is 2 hours? 120 minutes. You want to make sure that your units of measurement are all the same. If I was talking about 2 cups of sugar for this and 3 cups of sugar for that, but then I tell you he only has a pound of sugar. You have to convert. Everything needs to be in the same unit of measurement. It's easier for me to convert the 2 hours into 120 minutes rather than saying 10 minutes of work is 1/6 of an hour, or 15 minutes of work is 1/4 of an hour, right? We don't like to work with fractions as much. So convert your hours to minutes. So now we can write a constraint for the minutes. 15 minutes for each pie, 10 minutes for each cake. He only has 120 minutes to work. So that means this amount of time needs to be less than or equal to that 120. He can take all 2 hours if he needs. He just can't go over that. Okay. We know our next step is graphing this. So let's go ahead and rewrite. I'm going to subtract the 15x and then divide by 10. So that's going to give me y is less than or equal to. That would be a negative 15, then divided by 10. So that's going to simplify to negative 3 over 2x. That would have been a positive 120 divided by 10, which is just a positive 12. Okay. I'm going to go ahead and change colors for this and do different colors for different constraints. Okay. And so now we got the minutes taken care of. So now let's go to the sugar. 2 cups of sugar for each pie. 3 cups of sugar for the cake. He has 24 cups of sugar left. So that means he can use all 24. He just can't use any more than that. So this amount needs to be less than or equal to 24 cups. Again, let's rewrite it because we have to graph. Subtracting the 2x and then dividing by 3. That's going to give us y is less than or equal to negative 2/3 x plus 8. Okay, what's another constraint? Well, it says due to a typical demand, let me change colors again. Let's go green. Due to typical demand, he must make at least twice as many pies as cakes. Some of you love these things. Some of you hate these things. I don't hate them, but I'm not the best at them, okay? So I'm thinking to myself, he has to make at least twice as many pies as cakes. So that means pies is more than cakes. So that means that x, the number of pies, has to be greater than or equal to 2 times the amount of cakes. Because it says at least twice. So that means it could be twice as many, or the number of pies can be more than twice the amount of cakes. Okay, again, we know we have to graph this, so converting it, dividing by 2, I get y is less than or equal to 1/2 x. I also have another constraint that says he needs to make a minimum for 2 pies due to a pre-order. Pies, x, so that means x needs to be greater than or equal to 2. He has to make at least 2 pies. Also, again here, I know it doesn't state it, but he clearly has to make at least 0 cakes as well. So we can go ahead and add in that fact of y also needs to be greater than or equal to 0. He has to make at least something for a cake. So technically 4 constraints, but adding in that 5th one as well. Oops, sorry. Here we go. So now we know we need to graph. So I'm going to go back to this red color and graph the first constraint. So positive 12. Can I fit it by counting by ones? Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 10, 11, 12. So here's 12 and then negative 3 over 2. So down 3 over 2, down 3 over 2, down 3 over 2, down 3 over 2. It's a solid line. Here it is. Now I go to my next constraint, which was blue. Positive 8, that's here. Negative 2/3 slope. It's also a solid line. Okay. Green line. Y is less than or equal to 1/2 x. 0, positive 1/2. Okay, solid line again. And then the last one is going to be a vertical line. X is greater than or equal to 2. So I'm counting by ones along the bottom as well. So this is 2. So X is greater than or equal to 2. So it's there. We added that last one in, that Y obviously needs to be greater than or equal to 0. So that would be along the bottom. So all my things are graphed now, but now I need to worry about the shading. So for the red, I would be shading below the red. For blue, I'm shading below the blue. For green, I'm shading below the green. And for lavender, I'm shading to the right. And then obviously shading above that gray or black line that you see there. So shading below red, below blue, below green, and to the right of purple gets me in this feasible region. And so my next step is finding the vertices. So my vertices are going to be at here, 1, 2, 3, 4, because that is an irregular or some kind of quadrilateral, right? So I have 4 vertices, and that is at 2, 0, 2, 1. This is 2, 3, 4, 5, 6, 3, and 8, 0. Way easier this time. Everything was nice, whole numbers on the grid lines, perfectly awesome. So now that I know my vertices, I'm going to plug in those vertices into my objective function here to figure out what is going to maximize those profits. How many of each type is going to maximize those profits. So for 2, 0, let's say I have C equals 15 times 2 plus 12 times 0. That's going to give me a cost of 30, or a profit of 30. Next one would be 15 times 2 plus 12 times 1. That's going to give me $42. Then I have 6, 3. So 15 times 6 plus 12 times 3. That's going to give me $126. And then the last one is 8 and 0. So 8 and 0. And that would give me $120 profit. So what is the question asking for? To maximize the profit. So I want the maximum profit. So out of these $4 amounts, which one is the highest? Obviously the 126. So what is my answer? Not $126. My answer is how many of each type should he make to maximize those profits. So that means he needs to make 6 pies and 3 cakes to maximize profit. Okay. So kind of harder to define the variables and set up the constraints, but easier when it came to our vertices and plugging in to that objective function. All right, you need to go practice this on your own. I know it's very lengthy, but try one on your own, at least. All right, thanks.